Okay, guys, good morning. Last time we ended on page 9 with this recursive formula, which links OLBT to OLBT minus 1, right? And all we did here was to say that the balance at time t is equal to the balance at time t minus 1 minus the principal paid at time t. This we can see clearly on our amortization schedule. Then we went and replaced principal paid at time t by the total payment at time t minus the interest at time t. Next we went and replaced the interest by I times OLBT minus 1. And then put it all together. We see that both these terms have BT minus 1 in them. So we pulled out that, factored that out, times 1 plus I, minus R of t. So this is going to be a formula that comes in really handy every time we're looking for one of these, either BT minus 1 given B of t, or B of t given BT minus 1. Let's do the next problem that we see on page 9. It says, a $20,000 loan was made for 10 years at annual effective interest rate 5%. At the end of each year, $2,000 of the principal is paid, plus the interest that is due that year is paid separately. Find the formula for R of t. R of t being the total payment at time t. So, this is what I can do for this one. I realize that every year, I make a principal payment of $2,000. So B0 is equal to $20,000. This is the loan amount. Whoops. B1 is equal to 20,000 minus 2,000, because it says a principal of 2,000 was paid. B2, so let me just write 2,000 times 1. B2 is equal to 20,000 minus 2,000 times 2. Looking at this pattern, I see that BT is equal to 20,000 minus 2,000 times t. And BT minus 1, by the way, is 20,000 minus 2,000 times t minus 1. So then I go and I write an expression for the total payment, R of t, which is what they're looking for here. So R of t is equal to 2,000, which is the constant principal payment every year, plus I of t. So I'm using R of t equals P of t plus I of t, where P of t is constant every year. Go and replace this I of t by I OLBT minus 1. So I don't have to write OL anymore, just BT minus 1. And BT minus 1 is given by all of this right here. So go put that in. So it's equal to 2,000 plus I times this mess right here. 20,000 minus 2,000 times t minus 1. So I is equal to 0.05 in this problem. I can put that in right here, 0.05. So I get 2,000 plus 0.05 times 20,000 minus 0.05 times 2,000 t plus 0.05 times 2,000. And when I put it all together, I get 3,100 minus 100t. That's R of t. That's one way to do this problem. All they wanted was a formula for R of t, so I have my R of t. Right, let's create the amortization schedule for this. And you will be able to see from the payment column that it's equal to 3,100 minus 100t. Let's see. Let me just get a blank piece. So, continuing this problem, I'm going to create an amortization schedule. Let's call this page, what page is this? The previous page was page what, 9? Let's call this 9B. Okay, so time, payment, interest, time, payment, interest, principal, and OLB. So a $20,000 loan was made for 10 years. So L is equal to 20,000. That's my B0. So times 0. B0 equals 20,000. At the end of each year, 2,000 of principal is paid. So at time 1, payment, I don't know what it is. Interest, I don't know what it is, but I do know that a principal of 2,000 was paid. And that's the case for every year. And this goes on for a bunch of years. I'm going to stop at, let's say, 3. So since the interest rate is 5%, I will take 20,000 times 5% and put it here. 20,000 times 0.05 gives me $1,000. And they gave me the principal this time. So 2,000 plus 1,000, go backwards and create the payment, $3,000. That's the first payment. And then because the OLB here was 20,000, the next OLB will be this 20,000 minus the principal of 2,000 that was paid. So this would be 18,000. And I get this by just going 20,000 minus 2,000. Do it again. Now my OLB is 18,000, so the interest will be 18,000 times 0.05, $900. So the total payment was $2,900. And the outstanding loan balance at the end of time 2 is $16,000. It's just 18,000 minus 2,000. And this process continues. So look at this column. The next time around it's going to be 16,000 times 0.05, which is $800. And then 800 plus 2,000 would be $2,800. And just continue this process. So you can see that R of t is equal to 3,100 minus 100 for every time t. So at time 1 it's 3,100 minus 100. At time 2 it's 3,100 minus 200, and so forth. So looking at this column, it's obvious that R of t is 3,100 minus 100 times time t. Matthew, what's the matter?
Wait, why does it start with 3,100?
Because at time 1 it's 3,000. That means 1 times 100 has already been subtracted from some amount. At time 1 you took away 100 from something. What could you have taken away 100 from? 3,100, like that. Okay, so I'm going to just say look at payment column. There's another way to do this problem also, alternate solution. We know that B of t is equal to bt minus 1 times 1 plus I minus r of t. This is our recursive formula from the previous page. Recursive relationship. So r of t is equal to bt minus 1, 1 plus I minus b of t. All I did was bring the r of t to one side and everybody else to the other side. And I know from the previous page that b of t is equal to 20,000 minus 2,000 times t. Because every year I subtract a principal of $2,000, so at time t I have subtracted a principal payment of 2,000 times t. And I also know that b of t minus 1 is equal to 20,000 minus 2,000 t minus 1. So I'm going to go put those in here. So r of t is equal to bt minus 1, plug in now, 20,000 minus 2,000 times t minus 1, times 1 plus I, minus b of t, go put b of t back in, 20,000 minus 2,000 t. And clean this up. So you get 20,000. I'm multiplying everything by 1, minus 2,000 t minus 1, plus I 20,000. Thank you. Minus 2,000 I t minus 1, minus 20,000, plus 2,000 t. Let's clean this up. This way is pretty obvious right here that the payment is just 3,100 minus 100t. I just got caught up in the algebra here. It wasn't hard, it was just me not having multiplied by 0.05 in time. So the things didn't cancel for me right away as they should have. Any question? Okay. So then the next thing is I emailed you this morning just so you would have the page to write on for the problem that I wanted to do from 5.2, which is your at the back of the text. It says a 15-year adjustable rate mortgage of 117,134.80 is being repaid with monthly payments of $988.45 based upon a nominal interest rate of 6% convertible monthly. Immediately after the 60th payment, the interest rate is increased to a nominal interest rate of 7.5% convertible monthly. The monthly payments remain at $988.45, and there will be an additional balloon payment at the end of the 15 years to pay the outstanding loan balance. Calculate the balance immediately after the 84th payment. So timeline. This is going on for 15 years. And the payments are monthly. So 15 times 12 equals 180 months. So they're telling me that the interest rate is 6% initially for the first 60 months, but that's 6% a year, so I have to find the monthly rate. So let me say here, find the monthly rates. So I-12 over 12 is equal to 0.06 divided by 12, which is equal to 0.005 for the first 60 months, because this is going on for 5 years, right? Let's see. Immediately after the 60th payment, the interest rate is increased. So for the first 60 months, I have a rate of 0.005 monthly. So let's call that I-112. And then for the remainder of the time, I have another interest rate. I-12 over 12 equals 7.5% convertible monthly. So 0.075 divided by 12. So I-112 turns out to be 0.00625 after 60 months. Okay, now I have my rates. So let's mark this timeline off. If I start at 0, at time 60, here the interest rate is 0.005, and after that the interest rate is 0.00625 monthly. And the interest rate changes at 60, but they're asking me for the outstanding loan balance at time 84. They're also telling me that the monthly payments remain at $988.45, and there will be an additional balloon payment at the end of the 15 years to pay the outstanding loan balance. So let's call this 988.45 plus E, some extra payment at the last period. So because I don't know what the extra payment is at the end of the 15 years, I cannot use the prospective method. I have to resort to retrospective because I don't know what this payment is. So while if all these payments were the same, then I could have said OLB 84 is equal to the present value of the remaining payments. But I can't say that because I don't know the last remaining payment, right? So let's go backwards to retrospective. So retrospective, because we do not know E, the last payment. So OLB 84 equals what? What's the formula for retrospective? How do you do retrospective?
The loan balance value at that time minus the cumulative value of payments.
Right. The loan, L, minus the accumulated value of all the payments made so far. So the loan is 117,134.80. We better grow this loan, right? Not just the loan, but the loan grown to that time, 84, right? Accumulated value of the loan. So help me accumulate this loan. I have a loan here, L, minus L here. Help me grow this loan to time 84. Can you? How do you do retrospective? Don't you go L times 1 plus I to the K minus whatever amount S angle K, right? I'm trying to do that, but I have two different interest rates. Can you help me? Here's the loan. I want to bring this to time 84. Bearing in mind that the interest rate changes here. Can you give me an expression? Yes. 1.005 to the 60. Okay, now I'm standing here. Keep going. 1.00625 to the 24. Right? What's the difference between 60 and 84? 24, right? Okay, minus. You've made all these payments. So Can we accumulate those payments now?
Minus 988.5.
988.45, right?
That's,
Let's do these up to 60 first, right? Because they are at this interest rate 0.005. So how about 988.45 times S angle 60 at 0.005, and then grow it more. I'm up to here, so I'm talking about these payments up to 60. Let's forecast them 24 years. 1.00625 to the 24th power plus minus 988.45 times S angle what?
24.
Right, 24 at 0.00625. Do you see what I've done? I accumulated these payments, but that's the accumulated value at 60. The interest rate now changes, so I have to forecast that. And I have to find the accumulated value of these payments, these 24 payments, at this interest rate. What bothers you? Talk to me. Okay, when I clean this up, I got 183,480.995 minus, the next term gave me 80,087.559 minus 25,508.655. And the final answer was 77,884.78. So because these payments have to accumulate at 0.005, and then their accumulated value has to be forecasted at a different interest rate, I separated these payments from these payments. Tell me what bothers you, if something bothers you. Let's do the next one. Calculate the amount of interest in the 84th payment. So this is asking me for I-84. I-84 is equal to lowercase I times OLB 83. Right? How should I find OLB 83? I don't want to have to go through this retrospective because it's much more work. Couldn't I use OLB 84 to come up with OLB 83? Don't I have this? BT is equal to BT minus 1, 1 plus I minus R of T. Can I use that one? Can I say OLB 84 is equal to OLB 83 times 1.00625, because that's the interest rate prevailing here, minus R of T. What is R of T? R of T is the payment that's being made, right, at 84. So that's 988.45. So when I clean this up, for OLB 83, that's what I'm looking for. I will take my OLB 84, which is 77,884.78, plus 988.45. Let's bring this term over to the left side, divided by 1.00625. And that will give me OLB 83. and that turns out to be 78,383.334. Once I have OLB 83, I go and I plug in I-84 equals lowercase I, which is 0.00625, times OLB 83. And plugging this value in for OLB 83, I get 489.90. This way I didn't get all hung up in doing OLB 83 the way I had to do OLB 84 by accumulating the loan and then subtracting the accumulated value of all the payments made. I could just use the recursive relationship, and it took like a minute to get OLB 83 from OLB 84. Follow me? Okay. The last one says calculate the amount of the balloon payment. So how about, because the interest rate changes at 60, interest rate changes at t equals 60, let's find the tau equals 60 equation of value. That will simplify stuff a little bit. So I could do that. I could also look at this as saying, or view this as OLB 60 retrospective equals OLB 60 prospective. The OLB 60 is the OLB 60, right? So if I take the retrospective approach and set it equal to the prospective approach, both those values have to be the same. That would be the same as taking the tau equals 60 equation of value, setting it equal to 0. Follow me? So let's go. We start with this loan, L, which is 117,134.80. 117,134.80. Let's grow that to times 60. So 1.005, that was the prevailing interest rate for the first 60 months, to the 60th power, minus all the, so either you can make the loan minus and the payments positive, or the loan positive and the payments minus, but they have to be opposite signs, right? So minus 988.45, that's the payment made. Let's grow that accumulated value, S angle 60 at the first interest rate, 0.005. And why don't we set that equal to, I'm at times 60 now, set that equal to the prospective. So let's take the present value of the first 24 payments, or all the payments. How do you want to do it? However you want to do it. I can take 988.45 A angle. How many payments will be there left? Will there be left if I'm standing at times 60? I have 120 payments because I have a total of 180 payments. So 120 payments at the new interest rate, 0.00625, plus the last payment of E has to be taken care of. So E, and I want to discount 1.00625 to the negative 120. So this is what I would have if I were standing at times 60. This loan grown to times 60, the accumulated value of all of these payments to times 60, that accumulated value is equal to the present value of the remaining payments. So I took these 120 payments of 988.45. I found their present value by going A angle 120 times 988.45, plus I have this additional payment of E here, and that happens at time 180, so that has to be discounted 120 spaces, so I brought that back, and then I would solve for E. So that's the equation you would solve. Let's see, here for this term, I got 157,997.29, and minus 68,964.19 for this term, minus, let's bring this term over, 83,271.72 is equal to E times 0.47347. And therefore E turned out to be, let's see, 988.45 plus 12,168.42. That's E. But the question said, calculate the amount of the balloon payment. So the balloon payment is the total payment, which is 988.45 plus 12,168.42, which is the extra payment at the end. And so the final answer is 13,156.87. Is it clear? Any question on this? So this was an excellent use of the recursive formula, right? Shows you how that'll save you time. So I'm going to call this balloon payment is equal to 988.45 plus E, where E is some extra payment. Let's go to the next page. An amortized loan for $30,000 is made for 10 years. Okay, timeline. L equals 30,000 is made for 10 years. I equals 5%. The first payment is R, and thereafter payments increase by 300 each year. So first payment is R, second payment is R plus 300, third payment is R plus 600, and lastly, R plus 900. R plus 9 times 300. And what do they want? Find R. What do you say? Present value? What kind of annuity is this? Arithmetic. So present value of arithmetic annuity is given by what formula? I, P, Q, A, angle, N. I is equal to what? What's the formula? What's the formula for the present value? Yeah. Right. So can we plug in? 30,000, that's the present value, equals, what's your P? Right. It's called R. I don't know what it is. That's what I'm looking for. A angle 10 at 0.05 plus, what's your Q? I should write here P equals R and Q equals how much? 300, right. So R, A angle 10, 0.05 plus Q, 300 over I, 0.05 times A angle 10, 0.05 minus 10 V to the 10. So 30,000 minus, let's bring this term over, 9495.614365 divided by 7.217,34929. The answer for R turns out to be 2655.41. Totally doable. Let's do the next one. The next one is geometric. An amortized loan of $30,000 is made for 10 years at 5%. An initial payment R is made, and thereafter payments increase by 30% per year. So timeline. Here's time 0. At time 1 you have R. At time 2 you have 1.3 R. At time 3 you have 1.3 squared R. And at time 10 you have 1.3 to the 9 R. An initial payment R is made, thereafter payments increase by 30%. Find R so that the loan is repaid at the end of the 10th year. So same kind of thing, only this time you're going to do geometric. What's the formula for present value of geometric? P 1 minus
And then all of that over I minus U.
Right. So let's plug in. 30,000 equals, RP is called R, 1 minus 1 plus G, the growth is 30%, and divided by 1 plus I, so 1.05, raised to the 10th power, because this is happening for 10 years, divided by I minus G. 0.05 minus 0.30. Solve for R. So R turns out to be 30,000 times minus 0.25, if I bring this denominator to the left side, divided by this mess, which is minus 7.4633155526. And R turned out to be 1004.92. So those two are straightforward, right? Let's talk about replacement of capital. So what is this thing called replacement of capital? Look at what happens. I take a loan from the bank at some interest rate I, and the bank calculates what the monthly payment will be by going L equals some R, A angle N I, right? Are you following me? Amortization-wise, the bank calculates the payback amount. So every month or every year or every period, I pay back this amount to the bank, but the bank doesn't just take that amount and forget about it. What the bank does is, out of that amount, separate that amount into two pieces, like so. I need a paper to write on. Separate this payment into two pieces. The amount which will accumulate to L at time N gets put in a sinking fund. So now this is the bank putting it into a sinking fund. So Q, S angle N, J equals L plus the excess. You understand what I'm saying? The bank will take my payment, which I pay them back, and the bank, instead of just taking it and forgetting about it, will take that payment and separate it into two pieces. Some piece that's going to be needed to accumulate, to put into a sinking fund that will accumulate to L, because they are trying to replace their capital, meaning that how much should they put in a sinking fund at interest rate J, so that that amount, that constant amount that they take out from every payment R, this constant amount should accumulate to L. So this is Q equals L over S angle NJ. And then the remainder, R minus L over S angle NJ, is what's left over. That they keep. So replacement of capital is the process by which the bank will recoup the loan amount by putting a certain fixed amount into a sinking fund, which will accumulate to L at time N, and then the rest of the payment will go to them to do whatever they want. Are you following me? Whereas in the sinking fund method, it was the person who was borrowing the amount that was putting a fixed amount into their own sinking fund and paying back the bank only the interest, which was I times L. Now it's not the person who borrowed who's putting it into a sinking fund. Now it is the institution that lent out the money and is receiving the payments back from the borrower, which is taking the payment and splitting the payment into two pieces. One piece goes into a sinking fund to accumulate to the value of the loan. So that piece is going to be Q equals L over S angle NJ, because after all these Q's have to accumulate to L at time N. Plus, there's another piece of the payment which they get to spend. So the question usually is, what is the investor's, and the investor being the bank, what is the investor's yield rate? That's the question. How do you think I can compute this bank's yield rate? Talk to me. Let's say the bank lent out L dollars minus L. And let's say the bank is getting back some R. It's a monthly rate R that's coming back. And let's say that they take this R and they put it into a sinking fund. And the sinking fund deposit required is equal to L over S angle NJ. Can you give me an equation to find the yield rate of the bank? So what has the bank done? First, the bank has shelled out an amount L, right? So let's write that. Minus L plus the bank gets back some amount, R minus L over S angle NJ, plus the bank also gets back the L, but the bank gets back the amount L from the sinking fund at time N. So I have to discount that amount back to time 0. So L, 1 plus I to the minus N power equals 0. See if this makes sense to you. The bank has loaned somebody L dollars. That somebody is going to make a payment of R back to the bank. The bank will take that payment of R and separate that payment of R into two pieces. the piece that's required to pay back the loan, because it's going to accumulate to time at time n to the loan amount L. So that piece is equal to L over S angle NJ. The bank can't touch that because that piece is required to accumulate back to the loan amount. But the bank can touch the rest. It gets to keep R minus L over S angle NJ. That's profit for the bank, because that piece is not required to accumulate back to the loan amount, right? So when I write the yield equation for the bank has given out L dollars. The bank received this amount many times. How many times did it receive this amount? N times. So there should be a angle N, I, or Y for yield rate term here, because this amount that they get to keep is coming back many, many times as an annuity at some yield rate Y that I'm looking for, plus at the end of the term at time N, the bank is going to get L back from the sinking fund. So L, 1 plus I, which let's call this Y for yield rate right now, to the minus N power, equals 0. That's the equation for the bank, for the bank's yield. Are you following me or no? Do you have any concerns about this? So this is an annuity because this payment will keep coming in. So they get to keep R minus the amount needed for the sinking fund.